If you go back to memories of your high school algebra class, you probably saw this formula for compound interest at some point. It says that the future value of an investment is the product of the present value and the quantity 1 plus r to the t. Present value is the amount of money you start with, and future value is the ending amount. R is the interest rate, and t is the length of time you leave your money invested, whether in a bank or elsewhere. If this is a bit rusty, just hold on. We will explain what's going on. Take this example. Let's start with $100 and invest it in a bank that pays 4% interest per year. Notice I had to convert 4% to a decimal. Divide it by 100 to get 0.04. So the future value is 100 times 1.04 raised to the t. Simple enough to plug in the values of two variables. You may have noticed this looks awfully similar to y equals a times b to the x. This is the general form of an exponential function, as seen in previous lessons. In this case, our scale factor a is 100 and the base b is 1.04. Of course, the independent variable is x instead of t. This implies that money in the bank grows exponentially under compound interest. Make a spreadsheet of your own to verify these values. Here I have computed the future value of an investment at 4% interest over 20 years. If you need a reminder of how to exponentiate a non-integer base like 1.04, refer to the last lesson for more details. For comparison's sake, I have included a column for 7% interest and 10% interest over the same time period. Notice that at 10% interest, our investment at 20 years is over 3 times larger than that at 4% interest. And they both started with the same amount of money, $100. Here is a plot of those data points. This is consistent with what we have observed previously. The larger the base, the faster an exponential function grows. This also makes sense with intuition. There are two ways to make your money grow more. Either find a bank that pays higher interest rates, or leave the money in there for a longer amount of time. Besides R and T, it turns out there's another factor that can increase the future value. That factor is N, the number of compounding periods. You can see that this formula for compound interest looks similar to the first one we saw, except for the inclusion of a couple N's. What effect does this have? To find out, let's do a thought experiment. Suppose you went to a bank to invest $1,000 and the bank agrees to pay 100% interest. How much money will you withdraw at the end of 1 year? As we shall soon see, that depends. Bear in mind that no banks I am aware of pay anywhere near 100% interest. This aspect is a bit contrived, but it is an important part of our fictional thought experiment. So please bear with me. To start, let us suppose that the interest is compounded annually, once per year. That means at the end of the year, they pay you 100% of your initial $1,000 investment. So you double it and walk away with $2,000. Simple enough? But what if the interest is compounded semi-annually, twice per year? That means at the end of 6 months, they pay you 50% of your initial $1,000 investment, $500. So now you have $1,500. Another 6 months pass by, and they pay you the remaining 50%. But 50% of $1,500 is $750. So now you walk away with $2,250 total. Now consider interest that is compounded quarterly, 4 times per year. For simplicity's sake, let's start on January 1st with $1,000. 3 months elapse, and on April 1st, the bank pays you 25% of the initial $1,000 investment. That's $250, which makes the total investment $1,250, as seen in red. 3 more months elapse, and on July 1st, the bank pays you another 25% interest. That bumps the $1,250 up to $1,562.50, as seen in blue. 3 more months elapse, and on October 1st, the bank pays you another 25% interest on your current balance. That bumps it up to $1,953.13, as seen in green. The last 3 months elapse, and on January 1st of the new year, the bank pays the last 25% on your current balance. That leaves you with $2,441.41. Notice that we start with the same amount of money, $1,000, and the interest rate is the same, 100%. The only difference is how many times it is compounded in a year, and yet this has an effect on the future value. Let's break it down to see what is happening. In the last slide, we multiplied 1,000 by 1.25 4 times. 1.25 is the same as 1 plus 1 over 4. Interestingly, 4 is the number of times we compounded in that year. Remember that exponentiation is repeated multiplication. So we can say 1,000 times the quantity 1 plus 1 over 4 raised to the 4th power. This was found to be 2,441.41. This can be generalized to any number of compound periods n, as seen here. The future value is the present value, $1,000 in our example, times the quantity 1 plus 1 over n raised to the nth power. Applying that formula to these numbers, we get this data table. Look at the last row. If the interest is compounded every minute of the day for a year, our $1,000 grows to $2,718.28 at the end of a year. That interest was compounded 525,600 times because that's how many minutes are in a year, assuming exactly 365 days in a year. In another lesson, we will explain more on how to perform these calculations, so stick around for that. A plot of that data looks like this. Notice that eventually the graph flattens out around $2,718, as we saw on the previous screen. Interest rates and time can theoretically be made as large as you want, and the future value will grow exponentially. N can also be made as large as you want, but in contrast to interest rate and time, there are diminishing returns with this approach. That is seen by the flatness of this graph. To bring in some limit notation, we can say that the limit as n goes to infinity of the quantity 1 plus 1 over n raised to the nth power is approximately equal to 2.71828. In banking terminology, n going to infinity is called continuously compounded interest. This number 2.718 may seem rather strange, but it turns out to be so important that mathematicians have given it a name, E. We call this constant by the letter E. It showed up in a thought experiment on banking, but it turns out this number shows up almost everywhere. In the next several lessons, we will explore more of its significance, where it comes from, and how we can calculate its approximate value using computational techniques. If you have any questions thus far, please feel free to put those in the comment section below. Thanks for watching this lesson. I look forward to seeing you again.